So, hello everyone. Today I'm gonna present you our theoretical work regarding generating very high spin currents in manganese-based antiferromagnetic alloys. So first, I'd like to thank Western Digital, EPSRC, and the UM6P International PhD Program for their funding. So, before we start to dive deep in the subject, I would like to talk a little bit about antiferromagnets. So, in recent years, there has been a huge amount of research in antiferromagnets for many reasons. The first one is that they can be used for reading, as you can see here below. So, depending on the configuration of the two ferromagnets that are aligned vertically, we can stuck on the bottom an antiferromagnet which forces the direction of the adjacent ferromagnet, which means that we can have two different configurations and therefore two bits. So bit 1 and bit 0, which have different resistance. They can also be used for writing, and what we mean by that is that we can generate spin currents using a heavy metal, as you see here in gray. So this spin current can be injected into our antiferromagnet and therefore switch the local magnetization. And therefore we can have another state for the antiferromagnet. They can also be used for pinning the direction of the magnetization of an adjacent ferromagnet. So here, as you can see in the interface, the direction of the local magnetization in the interface of the antiferromagnet forces or imposes the direction of the magnetization of the ferromagnet, and therefore we pin this direction. And lastly, we can use them to actually generate spin currents using the spin orbit coupling. So we can generate spin currents using antiferromagnets, and these spin currents can be used to, for instance, switch the direction of magnetization of an adjacent ferromagnet. And this will be the focus of our talk. So how can we generate efficient spin currents? So for that, let's talk a little bit about spin orbit coupling. So spin orbit coupling is a relativistic effect where the deviation of the electron when confronting an atom with spin orbit coupling depends on its spin state. So for example, in this picture, as you can see, if the spin of the electron is up, it deviates to the right side, otherwise to the left. Well, it depends on obviously on the sign of the spin orbit coupling. And what happens macroscopically is that this can create what's called a spin current. So if you inject a charge current where you have many electrons, what happens is that electrons with some kind of spin, let's say spin down, will deviate to the left, and the ones with spin up will deviate to the right. And this creates the spin current, as you can see in orange. So we define what's called the spin hole angle is basically the ratio between these two. And our goal will be to maximize this quantity because we would like to apply as small of a charge current as possible and ultimately have a great spin current. So this will be the focus of our talk, this quantity. So the ratio between the two currents. So for that, we use several theoretical methods. And in our work, we focus on doping, the effect of doping and temperature. So we use what's called the green function, which is defined as follows. And we can use the green function to calculate many physical quantities, such as the density of states, the density, charge hole conductivity, and spin hole conductivity. So forget about these all formulas. The point here we want to make is that the green function allows us to calculate physical quantities. And we use a method, numerical method called KKR-CPA. So KKR stands for three scientists, Kohn, Rostocker, and Koringa. And CPA means coherent potential approximation. And what we do here is that instead of dealing with a material where we add up impurities, and therefore we will have to create many atoms, as you see here in the left side, what we do is that we replace every atom in the material by a kind of a mixture between the original atom and the impurity. And this allows us to have an effective potential and allows us as well to have very numerical advantages. Um, yeah. So the materials that we studied in our work are based on manganese platinum. So it has a very high Néel temperature of 1000 Kelvin, which means that the magnetic configurations can be maintained up to very high temperature. And here the opposite spin lattices are related by PT symmetry, which means that no Hall effects are no Hall currents are allowed. So this is the Brouwer zone of the system. And here on the right side, you see a typical curve of the charge conductivity. So here we plot the charge conductivity as function of the impurities. So here we are showing manganese, platinum, palladium. So the impurity here is palladium. And what happens is that near clean systems, we have that the charge conductivity is divergent, which we expect because we have a clean system without impurities, so less scattering. But around 50% of doping, we have a minimum of the charge conductivity, which is expected as well because this is kind of where we have lots of scattering events. Here in the red curve, you see the spin hole conductivity. So here the spin is along X. And again, what we see is that there are divergences near clear limits, but in the regime where we have impurities, it's kind of constant. And this is basically due to the fact that platinum and palladium, they have similar chemical structure, meaning that the band structure does not change really when we replace platinum with palladium. All right, so here we see the curve again that we showed earlier. And as we said before, the spin hole angle is defined as the ratio between the two quantities, so the red curve and the blue curve, and that's what we are plotting here. So when we divide the two curves, we get this curve of the spin hole angle, and what we see is that we get a maximum around 20% of concentration. So we decide to take this alloy where we get the maximum of SHA because our goal is to maximize this quantity, and we study the effect of temperature on that specific alloy, so which is manganese, platinum 0.2, palladium 0.8, which corresponds to the 20% of concentration. And what we see is that the charge conductivity and spin hole conductivity both decrease as function of temperature, but with a different rate, right? And this is what leads the spin hole angle to get a maximum, kind of a maximum around room temperature, so which is 8%. And this is good news because it means that it's practical. We can use this kind of material in real devices at room temperature. So next, we decide to replace this time platinum with iridium instead. So iridium is not chemically similar to platinum. It has one electron less than platinum. So that's why we decide to study this alloy, because we can see the effect of having another kind of a different, let's say, chemically structured element. And what we get is, again, the charge conductivity have divergences in the clear limit with a minimum around 50%. But for the spin hole conductivity, we can see an unconventional behavior where we don't have this kind of constant behavior in the dirty regime. And this is actually due to the fact that we are replacing an atom by a very different atom. So again, we divide the two curves and we get the spin hole angle, and this time we get the maximum of spin hole angle around 70% of platinum, and we reach a spin hole angle of 12%, which is very, very promising. So again, here we try to understand why we get this peak, these two peaks here, over here, and the minimum here. So that's why we do what's called a block spectral analysis, so which is defined as follows. So basically this is kind of a band structure, but which is k resolved. So you take the Brouwer zone Sorry, it's a kind of density of state, but which is K resolved. So basically, you take the Brillouin zone, you take a plane, and then you calculate your density of states in every K point. So this is what we see here. So what we see is that we get some sharp states around the gamma point for a concentration of 60%. The same for 70, the same for 80, but for the 75, what we get is that these states around the gamma point, they get scattered, which means we should expect a lower conductivity. And this is what's happening here for the spin-hole conductivity. So around 75%, we get this minimum, but then we get back to that kind of local maximum, which corresponds to the 80%. So which explains the two local maximum we get here. So to conclude the presentation, I would like to say that we have shown that dopant can enhance spin-hole angle in antiferromagnetic materials. And most importantly, that we have reached very, very high values of spin-hole angle in both alloys. So whether we replace platinum with palladium, as we have shown first, or when we replace platinum with iridium. And these values are comparable to the famous to the famous material which is famous for a high spin orbit coupling, which is platinum. So the value is 7%, but we got already 5% for this alloy and 12% for the other alloy. So finally, what I want to say, which is important, is that also temperature, we have seen the effect of temperature. And temperature does not, we have seen that it does not really affect spin hole angle. And therefore, these alloys can be really used practically in real life at room temperature. So thank you for your attention, and please can ask any questions. Any questions are welcome.
Thank you very much, Nabil, for the really nice talk. So the floor is now open for questions. You can either unmute yourself and speak, or you can write it down in the chat. Yes, Mahom and Frazli.
Hey, Nabil, thank you for your very nice talk.
Yes.
Actually, I just have a very simple question. In the beginning of your slide, you mentioned something, some temperature around 1000 degrees, which is 1000 Kelvin. So is it blocking temperature or is it like melt temperature of the your proposed material? Can you bring the first 3 slides in your presentation?
Yes, sure. Which one?
At the top left, you mentioned something around around 1000 degree
Here?
Kelvin, maybe.
Which slide?
Maybe before. Maybe second slide, slide number 2 or 3.
This one?
Not here. Not here.
The bottom?
No, before. Yeah, at the beginning of your presentation.
Yeah.
Again. Maybe here. Yes, this is slide.
Here, yeah.
The null temperature is 1000 Kelvin. Right?
Sorry again? Okay.
Null temperature Tn is 1000 Kelvin.
Yeah, 1000. Yeah, nail temperature. Yeah.
Okay, so can you comment something why it's like you very quickly you lose how you are losing like antiferromagnetism around room temperature?
So
By doping?
actually, that's why we have dealt with this antiferromagnet, because it has high nail temperature. So we didn't really care about magnetization at room temperature.
Yeah, I see. Okay.
So we haven't studied really the magnetization as function of temperature using our code.
Okay.
Yeah, we considered that the magnetization doesn't change that much from 0 Kelvin to 300.
Yeah,
That
then
is
it
our
will be
assumption.
very good if okay,
Well,
thank you.
nail temperature is 1000. I mean, especially
It's
the
very high.
magnetization is famous to have this straight line in the beginning, then it drops, right?
Yes.
Yeah.
So you are saying something very
So
high.
this is an assumption. It might be not true, but it's a theoretical work. I said it at the
I
beginning.
see. I see. I see. Okay.
Yeah.
Okay, man.
Hopefully it's
Thank
true.
you. I
We
hope
have
so.
another question on the chat from Joseph
Yes.
Soren.
So what's the question
And he
again?
says, why did you choose iridium as a doping element for platinum? And how did
Yeah,
you confirm that the doping element in platinum side?
good question. So if you see platinum in the periodic table, you have two elements. So you have four elements near platinum, but on top there is palladium. So palladium has the similar chemical structure as platinum because it's in the same column. But to the left side, you have iridium. And we wanted to compare the fact that we have a atom with the similar chemical structure. We saw the effect. So the spin hole conductivity in the dirty regime is kind of constant because we don't so we only vary the spin orbit coupling, let's say. But then when we replace iridium, we wanted to check the effect of changing the number of electrons. So when you change the number of electrons, many things can happen, such as shifting of the Fermi energy. Yeah, so you can have strange things happening to the band structure. So that's why we chose iridium and palladium. It doesn't come from nowhere. Yeah. I hope I answered the question. I don't know.
Okay, let's thank again Nabil for the very nice talk and